Welcome to our next topic in Geotechnical Engineering, and that is classification of soil. In general, there are two major categories into which the classification systems developed in the past can be grouped. So these are the textural classification, and the second one is the classification based on the engineering properties of or engineering behaviors of soil. So for the textural classification system, the soils are named after their principal components such as sandy clay, silty clay, and so forth. Shown below is the textural classification systems developed by the USDA or the US Department of Agriculture. This classification method is based on the particle size limits or the particle size distribution as described under the USDA system. So here are the following sizes for the principal components. So we have sand size. The sand size is 2.0 to 0.05 millimeter in diameter. For silt size, we have 0.05 to 0.002 millimeter in diameter. And for clay size, we have the diameter smaller than 0.02 mm in diameter. Okay? The USDA classification system uses this triangular textural classification chart. So we have here different classifications of soils, and as you can see from the three sides of the triangle, we have in this portion here, we have the percentage of clay, the percent of silt, and the percent of sand. So you just have to connect the line that is corresponding to the percentages of different components here. So let's take, for example, this one here. For example, we took a sample of 1 kilogram of soil from the site. So we have a 1 kilogram of soil sample taken freshly from the site. From this 1 kilogram of soil, we determine that it contains 35% of clay, 40% of silt, and 25% of sand for a total of 100%. So using the triangular textural classification chart, let's determine the classification of soil that was taken from the site. So first, let's look at this percentage of clay. We have the percentage of clay as 35%. So we locate where is the 35% here, and that is at this portion here. So this is the 35% of clay. Next one, we have 40% of silt. So the silt is on this side, and we will locate where is the 40% here. And that 40% is this portion here. And take note of the line here. We had a horizontal line because the lines here are horizontal. This one is slanting. So let's follow the slant of the line and draw a line from the 40%. So we have here. Okay. And then for the sand, we have 25% of sand. Sand is at the bottom of the triangular classification. And let's look for the 25% here. And that 25% is located at this portion, and follow the slant of the line. And we have here. So to where the three lines intersect, that is the classification of the soil. So the intersection of the three lines is located here at this portion, and that is pointing to a classification of clay loam. Therefore, the soil taken from the site is classified as a clay loam. So that's how we use this USDA triangular textural classification chart. The challenge here is, so it's easy to use this triangle, this chart, but the challenge will be computing for the percentages of clay, silt, and sand. Now let's go to the classification by engineering behavior, and it is divided into two. The first one is the USCS, and that is the Unified Soil Classification System. And the second one is the AASHTO, or the American Association of State Highway and Transportation Officials. So let's differentiate these two classifications. Now the question here is, what is the difference between the two major category, which is the textural classification and the classification based on engineering behavior? As discussed earlier, the textural classification is based on the particle size distribution of the soil, the particle size distribution. Now for the engineering behavior, yes, it also have the particle size distribution. So it considers the particle size distribution, as well as the second one, it considers also the plasticity of the soil. So particle size distribution and the plasticity of the soil, which is missing in the textural classification. Okay? So let's start with the Unified Soil Classification System, or that is the USCS. So how do we use this classification system? This system classifies soils into two broad categories. We have the coarse-grained soils and the fine-grained soils. So coarse-grained soils are gravelly and sandy in nature, with less than 5% passing through number 200 sieve. So what does it mean? So if we have here our sieve, so it says there, less than 50% passing through the number 200 sieve. If we imagine this, it means that if we put here soil, so we have here soil. If we put here a soil, obviously, as you can see from the mesh here, some soil will pass through this mesh. So from the definition of a coarse-grained soil, it says there, less than 50% passing through the number 200 sieve. So if there is less than 50% passing, it means there is greater percentage retained on this mesh or in this sieve. If this is sieve number 200, if this is sieve number 200, it just means that what passes it, or the soil that passes it, is 50% or less than 50%. So for a good number, let's say, what retained here is 60%. Okay, 60%, and then what passes it is 40%. Meaning, there are much greater particles here that is retained. If there is more particles that is being retained, therefore, we can conclude that the soil sample is gravelly or sandy. Meaning, there is more bigger particles there is than the smaller particles. because more percentage is retained compared to what passes through the mesh. So that defines a coarse-grained soil. Another one is the fine-grained soil. Fine-grained soils are with 50% or more passing through the number 200 sieve. So in here, we have 50% or more passing through number 200 sieve. So if this is the sieve here, number 200 sieve here, okay? So instead of having a 60%, 40% there, we can say that what passes here is 60% and then what is retained is 40%. Meaning, there is more particles that passes through the wire mesh here. So, if we visualize it, there is more finer particles compared to a coarser particles. And thus, it is defined as fine-grained soil. The group symbols start with prefixes of M, which stands for inorganic silt, C for inorganic clay, or O for organic silts and clays. The symbol PP is used for peat, muck, and other highly organic soils. So here are the other symbols used for the classification. We have the well-graded, poorly graded, low plasticity, that is liquid limit is less than 50. H is for high plasticity or liquid limit is more than 50. Okay? Now in this classification system, unified soil classification system, we can use two. So previously, we used only one for the USDA, and that is the triangle. Now for the USCS, we use two. We use the flow chart. So this is the flow chart for the coarse-grained soil. So it says here, less than 50% passing number 200. Less than 50% passing number 200, we can also rewrite that or define it as greater than 50% retained. You can also define it this way, greater than 50% retained number 200 sieve. And the next one here, flow chart for the organic fine-grained soils, which is defined as greater than or equal to 50% passing number 200 sieve, or we can define that as less than 50% retained number 200 sieve. Okay, so let me show you how these two flow charts will be used later on. So this is one of the ways we can classify soil using USCS. The other one is by the table, the USCS table. Here you can observe that you can find it is divided into two also. We have here the coarse-grained, so the coarse-grained and the fine-grained. So if you follow the instruction, it says here, coarse-grained soil more than 50% retained number 200 sieve. Fine-grained soil 50% or more passes number 200 sieve. And then if you satisfy the criteria from the beginning, from this left side, you proceed towards the right, okay, until you find the right classification of the soil. So we can discuss more on that through the examples. There's also the parameters here needed. As you observe from this table and the flow chart, so from the flow chart here, we need to solve for the, you see here, the CU and the CC. Okay, the C sub U, CU, or and the CC, or the C sub C. How do we solve for the CU and CC? Because it's also found here in the table, you also have CU and CC. The good thing about the table is that it already gives the formula. So there's no need to memorize the formula if this table is given. But if the flow chart is given, there's no formula there. So it's still good to memorize the formulas. So what are those formulas? So we have the CU and the CC. For the CU, it is defined as the uniformity coefficient, or the CU. For the CC, it's defined, or it is named as coefficient of gradation or coefficient of curvature. Thus, it is CC. The formula is C sub U is equal to, let's make it bigger. Okay, there you go. C sub U is D60 over D10. For C sub C, we have here D30 squared over D60 times D10. Now, what are these D60, D10, and D30? Now, take note of this one here. D10 is the effective size. This parameter is the diameter in the curve corresponding to the 10% finer. The effective size of a granular soil is a good measure to estimate the hydraulic conductivity and the drainage through the soil. Okay, so this is the diameter that corresponds to the 10% finer. Okay. So if we compute for the percentages of the what is retained, or what passes in the sieve, so the 10% finer there, the 10% passing there, so the diameter that is corresponding to the 10% finer, that is the effective size. Okay, I will show you that later in the example. Same is true with the D60 and D30. D60 is the diameter that corresponds to the 6% finer, and D30 is the diameter that corresponds to the 30% finer. Now, if the question is asking for the sorting coefficient S sub O, we have S sub O equal to square root of D75 over D25, where D75 here is the diameter corresponding to the 75% finer, and D25 is the diameter corresponding to 25% finer. Okay, so these are the things that you need to classify the soil using the USCS. Let's go to the second classification under the classification based on engineering behavior of soil. We have the AASHTO, or the American Association of State Highway and Transportation Officials. According to the system, soil is classified into 7 major groups, A-1 through A-7. Soils classified under groups A-1, A-2, and A-3 are granular materials, of which 35% or less of the particles pass through the number 200 sieve. Soils which more than 35% pass through the number 200 sieve are classified under groups A-4, A-5, A-6, and A-7. These soils are mostly silt and clay type materials. To classify a soil according to the table below, one must apply the test data from left to right. Same is true with the USCS. We apply it from left to right. By process of elimination, the first group, so take note of this, the first group from the left into which the test data fit is the correct classification. Okay? To evaluate the quality of a soil as a highway subgrade material, one must incorporate a number called the group index. Don't forget putting group index in your soil classification under AASHTO with the groups and subgroups of the soil. This index is written in parentheses after the group or subgroup designation. The group index is given by the equation, so this is to be memorized if it's not given in the problem. So this needs to be memorized. Group index or GI is equal to F sub 200. What is F sub 200? That is the percentage passing number 200 sieve. Okay? So F sub 200 minus 35 times 0.2 plus 0.005 times liquid limit minus 40. Okay? So that's the first term. Next, the second term here is 0.01 times F sub 200 minus 15 times plasticity index minus 10. Okay? So, group index is divided into two terms. So, what are these two terms here? Okay? So, this is the table for the AASHTO, which we will be using later on. Again, you can observe that it's divided again into two, wherein we have the granular material, also known as the coarse-grained, and the silt clay materials or the fine-grained soils. And you can see that there is an instruction, it says there, 35% or less of total sample passing number 200. And for the fine-grained soil, we have more than 35% of total sample passing number 200. Okay? So that's how you start your classification. Okay, for the formula, the first term there is, wherein this is the first term of the formula a while ago. It is the partial group index determined from the liquid limit. Okay? And the second term is 0.01 F sub 200 minus 15 Pi minus 10. It is the partial group index determined from the plasticity index. Okay? So again, from this formula of GI, the first term is for the liquid limit, considering the liquid limit, partial group index. And the second term is a partial group index, considering the plasticity index. Here are the rules in determining the group index. It is something that you need to familiarize yourselves. The first one, if the equation yields a negative value for GI, the GI is taken as 0. Okay? So meaning there is no negative value for the GI after the parenthesis. For example, we have here A-1-B parenthesis -1. No, you must not put -1 there. Rather, you will put there 0. Okay? So that's an example. The next rule is the group index calculated from the equation is rounded off to the nearest whole number. For example, if GI is 3.4, you must round off to 3. If GI is 3.5, you must round it off to 4. Okay, so GI should be a whole number. Next, number 3 rule, the third rule. There is no upper limit for the GI. Number 4, the GI of soils belonging to groups A-1, A-1-A, A-1-B, A-2-4, A-2-5, and A-3 is always 0. So, this is already a shortcut. If the classification falls on A-1-A until A-1-3, it is already 0. So, let's go back to the table. So, where can we find that? So, here are the those mentioned. We have A-1-A, A-1-B, A-1-4, A-1-3. Okay. And let's look at that again. How many? So we have 1, 2, 3, 4, 5. So A-2-5 is included. So A-2-5. So 5 of them. If your classification falls into them, therefore your GI is 0. So put there GI equals 0. Okay. If it falls there. Next, number 5. When calculating the GI for soils that belonging to groups A-2-6 and A-2-7, use the partial group index for PI, or that is GI is equal to 0.01 F sub 200 minus 15 times PI minus 10. So that is if it falls here. So use the partial GI considering the PI. Okay? So, the one that is wherein PI is considered. Now, how about the rest? How about if the classification falls in this category? A-4, A-5, A-6, A-7. Then, you are to use the whole GI. So, GI as the whole. Or wherein the two-term formula for the GI. Okay? Again, use GI is equal to 0 here. Partial GI, considering the plasticity index. And here we have GI as a whole. Okay. Right? So, for complete reading, read our textbook here. Okay, so let's solve for the following examples to fully understand the classification. Let's solve for examples. Okay, we have here number 1. So all in all, we have how many examples? 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so we have 8 examples, and we will divide this video into 2, part 1 and part 2. For number 1, the result of the sieve analysis is shown below. So we find here the sieve number, the diameter of the sieve, the spaces, the mesh. And then we have here the mass retained. So what is this mass retained? So again, let's go back to the drawing here. Let's go back in this drawing. So these are the stacked sieves. So obviously, the lesser spaces of sieves is located below the at the lower part. So we can name this as, so the bigger number here signifies the number of the wires or the mesh in the sheave. So meaning the greater the number here, the sheave number, so that's the number of mesh that you can find. So the greater the number, the finer the opening of the mesh. Okay? Therefore, number 200, sieve number 200 has the finest opening or the smallest diameter from these sieves. Okay? The diameter for sieve number 4 is 4.76 mm, whereas the diameter for number 200 is 0.074 mm. Okay? So you can now understand why if we stack the sieve, you will locate number 200 here, whereas you will locate number 4 here. So that's how you stack the sieves. Right? Now, again, let's go back to explaining what does mass retained means. Mass retained here means that if you pour your soil here, for example, a 1 bag of 1 kilo of soil, you pour it here, obviously the finer particles will go down and the larger particles will remain on the sieve wherein it cannot pass through. Okay? So there are particles that will be left in the sieve, there are particles that are left here. What we mean is they are retained in these sieves. Thus explains the mass retained. In sieve number 4, if we take out sieve number 4, it contains 25 grams of soil. If we take out sieve number 40, it has 180 grams of soil, and so on and so forth. Okay? So, let's delete here. Right. How do we solve now this question? What percentage of the soil is retained in number 200 sieve? Then for letter B, what is the effective grain size in mm? What is effective grain size again? As mentioned, it is D sub 10. The diameter at the 10% finer. It's asking for the diameter in mm. Now letter C, determine the uniformity coefficient, or that is C sub U, or the CU. Okay, let's go first for the number 200 sieves. How do we compute for the percentage retained here? At this portion here, percentage retained. What it means by percentage retained is that if we concentrate on the sieve number 200, so if we concentrate on sieve number 200 here, what is the percentage of soil that can be retained in number 200 sieve? So meaning, in the total of 1 kilogram of soil, how many, in the example, we have there total of, no, it's not total yet. Okay, so how many percentage it is, that is, if it is retained, so that is percentage retained in number 200. So how do we get the percentage retained here? If if only 85% is the gram that passed through number 200. That means if we total this, so what's the total? Let's go to this one. So if we put here the total, for us to fully understand, so that is 25 plus 80 plus 110 plus 160 plus 180 plus 220 plus 380 plus 590 plus 110 plus 85, so that is for a total of 1940 grams. For a total of 1940 grams, okay, what passes for number 200? So, this is number 200 here. What passes only here is 85 grams. 85 grams because 85 grams is what went to the pan. So, if what we put here is 1940 kilos, grams, I should say grams. We put here 1940 grams of soil. So, how many grams of soil is retained? So, that is 1940 minus 85. So, this is 1855 grams retained. And what is being asked in the question here is the percentage retained in sieve number 200. Therefore, we can have here as 1855 grams divided by 1940 times 100. Because this is what retained. This is what remains in the number 200. If you remove the other sieves, 1855 grams will be retained in number 200, and what passes only is 85. Therefore, if we compute it, it will be 1855 divided by 1940 times 100, and that is okay, so that is 95.62 numbers, okay, 95.62%, because this is what retained. Okay, if it is asking for the percent finer, meaning this is what we are concentrating here. To illustrate it, I'm trying hard to illustrate it. So this is retained, and then this is finer or passing. Okay, so percent. So let's have a summary. So for percent retained, we have here equal to 1855 divided by 1940, because this is the total. This is the total soil times 100, and that is equal to 95.62%. If what is being asked is percent finer, percent passing, also known as percent finer. Okay, so this is similar, or percent passing, percent finer is the same. That is equal to 85 divided by 1940, and that is equal to 4.38%. So 4.38%, and that is percent passing or percent finer. If you add these two, that is plus 95.62 that is equal to 100%. Okay? So let's use the formula here in solving the problem. It's asking for the percentage of the soil retained in number 200. Therefore, percentage retained is equal to the total minus the accumulated here. The accumulated here is what we have computed is 1855, right? And this is the one that passed. Or we can just say, let's leave it there. Or let's just say this is 1940 minus 85 all over 1940 times 100, and that is equal to 95.62%. Okay? So the way I presented it is for you to have idea on what ways you can also solve this problem, okay? Or the principle behind solving the percentage retained. Okay? Let's go to B. What is the effective grain size in mm? So, how do we determine the effective grain size? So, let's find the percent finer. Okay? The percent finer, 10. Again, what is percent finer? The one that is passing the sieve. Okay. So, if we want to do that, then let's compute here the percent finer, or the percent passing. Okay? So, how do we compute for the percent passing? It says there, the one that passes it. This is 85 here. This is 85 grams that pass out of number 200. And we have here 4.38. So, we put here 4.38%. Or just 4.38. How about pan? Does it have soil that passes through the pan? No, it has 0% of soil that passes through the pan. Now, the question here is, how do you compute for percent finer of number 100? So, percent finer number 200, we have here 19, we have 85. So, we have 85 over 1940 times 100 equals 4.38%. Percent finer for number 100 is equal to 85 plus 110 over 1940 times 100, and that is equal to 1940 times 100. So that is 10.05. So that is 10.05%. Now, how about the percent finer number 80? So that is 85 plus 110 plus 590. So this is 8. So this is 80. So we are adding this because this is the grams. These are the grams that passes through number 80. Okay. So we have here 590 divided by 1940 times 100 equals 0.05%. So we just add it up here in our calculator. Plus 590. That is equal to 40 40.46%. So here we have here 40.46%. And so on and so forth. So let's put here 60.05%. I hope you got the idea. 71.39%. 80.67%. 88.92%. 94.59%. And then we have 98.71%. Okay? Now, the percent, 10% here is 10.05. So, what's the diameter that corresponds to the 10%? So, that is 0.149. If we accept this already as the 10%, then the answer already here is 0.149. Okay? So, it does not necessarily mean that if our answer is 0.149, then D10 is D100. No, it's not. D10 is the diameter corresponding to which of the percent finer here you can locate the 10%. The 10% is found here, then diameter is somewhere here. So that's how the idea is. So you can have there, therefore, D10 is equal to 0.149 mm. If we accept 10.05 as the 10%. Okay? Next, letter C. Determine the uniformity coefficient. So, uniformity coefficient is CU. CU. So, again, what's the formula for the CU? The formula for the CU is located here. There. It's D60 over D10. Okay? So, CU is equal to D60 over D10. We were able to locate D10. How about D60? Okay, from the graph, okay, so there is a percentage here that is near D60. And that is this portion here. D60 has a diameter 0.25 mm. Okay? So, we now have here D60 is equal to 0.25 mm. Actually, we are just somewhat lucky because it's already there in the table. But if 60% is not found here, if you cannot have the 60 and the 10 here, you will either graph or solve for the value of 60 and 10%. Okay? So, CU is equal to 0.25 divided by 0.149. That is equal to 1.68. Does it have a unit? No, it does not have any unit. Okay, so that's for number 1. Now let's go to the question number 2. A soil has the following particle size distribution. Gravel is 20%, sand is 10%, silt is 30%, and clay is 40%. Classify the soil according to the USDA textural classification system. Okay? That's going to be easy if we have only 3. But the problem here is it has gravel in it. Remember the triangle system a while ago? It has their clay, the clay, silt, and the sand. There's no mention of gravel. So how do we solve this with the gravel in it? Therefore, what we will do here is to modify the percentages. So modify it wherein what you are going to take as a 100% is representative only of sand, silt, and clay. So let's modify. So modified percentages of sand, silt, and clay. So this is a total of 100%. What we need as a 100% is the sand plus the silt plus the clay equals 100%, isn't it? But here we have gravel. So what will we do? So modified percent sand equals, the percent of sand here in the example is 10%. What we need to do is, from the 100%, you subtract the percent of gravel. So, here you put here the percentage of sand, then the denominator is 100% minus the percent of gravel. So you now have here 10% all over 100 minus 20%. So that is equal to 12.5%. Next, we have the modified percent of silt. That is equal to the percent of silt, which is 30%, over 100 minus the percent of gravel, which is 20. So, modified percent of silt is equal to 37.5%. Then we have here the modified percent of clay. We have here percent of clay is 40%. All over 100 minus percent gravel, 20. So that is equal to 50%. Okay? So we now have here the percent of sand, percent of silt, and the percent of clay. And now let's go to the triangle. Let's use this. So for the sand we have, so this is the sand, we have 12.5%. So we have here the sand. So let's make it bigger. 12.5% of sand. This is 10. This is 20. In between here is the location of the 12%. This is 15. So therefore, we can say that 12 is somewhere here. Say here. That is 12.5%. How about the other one? We need the percent of silt. We have 37.5. 37.5 silt. Here is the silt. So that is between 30 and 40. 37. So this is 35. So can assume that the 37.5 is located here. Okay. Take note that the slant of the line is based on the given slant here. Okay, so here is the 37.5. And then finally, we have the percent of clay, 50%. So 50% and clay is located here, 50% is this point here. So to where they intersect, that is the location of the classification of the soil. And in here, the location of the intersection is in the clay region. So this region here belongs to the clay. Therefore, we can say that the soil is clay. Okay, therefore, soil is clay based on this classification here. Now, what happens if the three lines does not intersect? It means there needs to be a problem with the solution because these three lines need to intersect with each other. That's how you locate the classification. Okay, so that's for number 2. Okay, you can screenshot. That's for number 2. Okay, now let's go to the example number 3. For example number 3, we have here the given data. Shown is a sieve analysis of soil samples A and B. So we have here the sieve number, we have the diameter of the sieve, and the percent passing or the percent finer of the two soils. We also have here the liquid limit and the plastic limit. The question here is, first one, classify soil A using AASHTO method. Next, classify soil B using AASHTO method. Okay? So, how do we classify using AASHTO? Remember that we only have one tool. We have the tool here, the table. So, let's use this table. Again, what's the rule for the using the table for the AASHTO? So again, there's the rule. Okay. Where's the rule? And here. It says there, the first group from the left into which the test data fit is the correct classification. Okay, so let's go back. Here. So from the table, observe that you need to choose first between the two table here. Are you going to use this one or this one here? So that's the first step. Choose between the two. The first one, it says there, 35% or less of total sample, passing number 200, granular material or coarse grained material. Then the next one is more than 35% of total sample, passing number 200. Okay? Now, it mentions number 200. What is the percentage on number 200? For soil sample A, the percentage of 200 is 4%. What does it mean? The percent passing number 200 is 4%. Meaning, if this is the sieve number 200, the material, for example, the 1 kilo material, what retained here is 96%. What passes here is 4%. What can you conclude from this figure? We can conclude that the soil sample is a granular classification. It's in the granular or the coarse-grained side. So only 4% passes the number 200. Therefore, we are to choose the granular because 35% or less. So 4% is here. 4% is included here. 35% or less, the 4% is included there. Okay? Next. So after you choose which one between the two, what's next is look on the number 10. So number 10, what's the percent on number 10? Here is the number 10. Percent passing is 54. Let's go back. Number 10, 54. Max. For classification A-1-A, it says there, percent passing is 50 max. Does it satisfy that condition? No, because the percentage passing number 10 is 54. So, it should not be 50 max, it should be 50 minimum. So, if this is X here, therefore, this one here is correct. It's blank, well still, it's correct. Okay? Now, after number 10, the next one here is number 40. Let's go to number 40. Okay? Number 40 here. There. Percent passing is 22. Let's go there. So, is 22 satisfies the condition 50 max? Yes. So, it is within the limit. 22 is within 50 max. Okay? It's good. Now, let's go to number 200. For number 200, here, percent passing number 200 is 4%. Let's go back to the table again. Does it satisfy the condition 25 max? Yes, again. Because 4% is within 25 max. Okay? So that's good. Now, let's go to the next one that we need to look at. The characteristic of the fraction passing number 40. Let's see the liquid limit and the plasticity index. Liquid limit first. How is the liquid limit here? Liquid limit is blank. So, meaning, this one here is acceptable. Okay? If it's blank, then it's maybe 0. Then, again, there's no category here, so it's still acceptable. Next, we have the plasticity index. Plasticity index, we have here the PL. We have PL here, but still 0. So, remember that plasticity index is equal to LL minus PL. 0 minus 0 is still 0. So, how is it here? It says here 6 max. Is 0 within 6 max? Yes, indeed, it is. Okay? So, what does we conclude now? We therefore conclude that the classification of the soil A is at A-1-B. Okay? Because you can see the check marks here. So, it means, so at A, it is a, how do we put here? So, using the table, oh, by the way, we forgot the GI. Remember that the classification should have a GI. So, what's the rule about the GI again? So, if it belongs here, GI is equal to 0. Okay, so GI is 0. So we have here the classification A-1-B. And that is parenthesis 0. Okay. So it's just based on the table. Okay, now let's go to letter B. So the soil B. Okay, so let's use this fresh table for the soil B. Now for the soil B, let's again start from the selection. Are we going to use granular or are we going to use the fine-grained or the silt clay? Again, let's observe what is at number 200. So at number 200, we have here percent passing 33. Okay. So if that is percent passing 33, then this is the number 200. What passes is 33%. So what retained here is 67%. What can we conclude? It is a coarse-grained material, meaning there's much greater mass retained compared to what passes. Okay? So we are going to also read here 33. 33 is belonging here, 35% or less. Because here we have more than 35, therefore we are using granular material. Next, let's observe number 10. For number 10, the percent passing, for number 10, the percent passing is 77. So, is 77 satisfying this criteria here? 50%, 50 max. No. So, let's go here again. Next, let's go to number 40. So, for number 40, what's the percentage passing on number 40? We have 51%. So, 51%, does it satisfy the criteria 50 max? So, again, it is 51%. And then in A-1-B, 50 max? No. It goes here, 51 minimum. Again, it's correct here. Let's go to number 200. Number 200, we have percent passing 33%. So, let's see here. Is 33% fitting the criteria 10 max? No, X. So, it goes to the 35 max. So, check, and then check this one. Okay. Next, let's go to the liquid limit. The liquid limit here is 46. So, is 46 fitting on the criteria 40 max? The answer is no. It should be here in 41 minimum. Okay? So, check, and then check on the 35 max, and then check on the 41 minimum. Next, let's go to the, it's the next one. It says there, plasticity index. So, let's solve for the plasticity index. PI is equal to LL minus PL. LL is 46 minus 29, and that is equal to 17. Yeah, 17. So, PI is 17. Okay? So, again, The PI here, does it satisfy 10 max? No. It's in the 11 minimum. But, let's check for the other criteria. This is check for the 35 max. How about 40 max? Again, the same as what happened here. This is X. Okay? Now, let's go to the next category. For A-7, check. 35 max. 41 minimum, because we have check mark here. 41 minimum and 11 minimum. Okay, finally, we were able to find out that the category here is, or the classification is, A-2-7. Okay? Therefore, that is the classification. So, therefore, it is soil. Okay. Soil is A-2-7. The question here is the GI. Again, let's go to this study guide. So, we need the partial GI. We need the partial GI because we are in A-2-7. We need the partial GI considering the PI. Okay? So, the formula for GI here, and we only need the PI portion. The PI partial GI, so we don't need the first term. We only need the second term, the PI one here. So let's compute for the GI. GI is equal to 0.01. What is F200? F200 is the percent passing number 200, and that is 33. Okay? So we have here 33 minus 15, and then PI, we computed PI a while ago as 17 minus 10. That is equal to, that is 1.26. Again, remember that it mentioned that it should be in whole number only. Therefore, this is approximately equal to 1. So, soil is A-2-7, parenthesis, or GI is 1. So, this is the final answer. Okay? So, that's for number 3. Okay, so, let's solve for the rest of the examples in the part 2 of the video.